The history of the world has been shaped by revolution. Revolutionary discoveries, revolutionary inventions, revolutionary ideas.
This is part of British Leyland's sales promotion for the 1982 Motor Show. Everything you see, from the banks of slide projectors to the robot arm, is being controlled by a microcomputer. Well, here's a more modest vehicle. It's the BBC's robot buggy, and it's being controlled by a micro. Well, it's following this black line, trying to find its way out of the maze, and also trying to find this light over here. Well, we'll see how it's getting on and how it works a bit later on in the programme. But how can we get a micro to sense what's going on around it and then control a piece of equipment? Well, let's dig into it a little bit. It's not quite as difficult as it seems. Well, with me today again is John Coll, who's going to dig into these mysteries. John, what's the setup here?
Well, we've got a digital setup here, Mac. We've got a games paddle with a switch on it and a set of lights. And when I push the switch, the lights, as you'll see, change. So, everything digital, just ons and offs here. And this games paddle switch assembly plugs in here. We've got that plugged, in fact, into the analog input, but we're actually feeding digital signals in. We've got a couple of other studio feeds, special connections there, but that's the main digital input. And then these lights, they're being plugged in underneath one of the output sockets, this one here. Those 8 cables feed into that output socket. All those devices are addressed from the memory map of the computer. Remember that we had a memory map, 64K memory map, and we used this display to illustrate.
Right, each one of these is a byte running across with 8 bits, and there's about 65,000 in the machine itself. Well, what happens inside the computer?
Well, we've got a couple of those addresses set aside, not for RAM, random access memory, but in fact for input and output devices. And here's one particular address, 65,088, which in fact is an input connection. And when I push this button here, the bit changes, and if you push the button on your games paddle, a different bit changes. So the input from this is being fed into this address, and we can sense it there. And the output is at another address. These lights are connected to address 65,120. And you can in fact see that there's a mapping between, or a relationship between, the zeros and ones here and the lights here.
These 2 addresses here will be quite different on other machines, but I suppose that they have them, a similar sort of thing.
Well, yes, you must have on any computer system some way of getting digital information in and some way of getting it out. But as you say, there will be actual different addresses in different machines. And you have to have some command for getting information in, getting information out. On most computers, the command for reading information in is called peek. And this statement, n equals peek of that address, means put into the variable n the value that you find in address 65,088. And the command on most computers for getting information out is to poke or put into that address, 65,120 on our machine, a number. And the number we've got for the moment is 108.
Which is stored in that location, obviously, in binary.
That's right. Right. Now, on the BBC computer, we don't use peek and poke. We have 2 different phrases. This is the phrase for input, and this question mark followed by an address is read as the contents of 65,088. And it says n equals the contents of, so it transfers a number from that address into the variable, which we called n in this case. And going the other way, we say the contents of 65,120 equals, in this case, 108. So the number 108 goes out. Now, we can actually transfer information out of the computer in various ways. We can alter this number, and then that will alter the lights. For example, I can set a random number. Let me just show you again. If I push a random number into 65,120 by pushing a key on the keyboard, it will change the lights. But you'll notice that a number 1 here corresponds to a light on here. Or if I put 0 into that address, then all the lights go out. Now, not only can I do it in that way, I could actually type a number in. If I type the number 18 into the machine, 18, and press return, then 18 decimal gets put into this location and appears on the lights.
That's a 16 and a 2, which is 18.
That's right, the binary representation. Right. And we can also, of course, use the games paddle again to affect the input, and then the input can affect the output. Now, we're actually running a program at the moment, but I could stop the program and talk directly to that location. I can say the contents of 65,120 equals some number like 255, for example, and that turns all the lights on. That's the biggest number you can store in that one byte.
So we can put digital information in it, we can switch on the lights here.
That's right.
So what?
So what? Well, you've got 8 control channels here. You've got 8 signals which can be switched on or off, and you could use those to control 8 devices.
So in effect you could make that turn the robot left, and this one turn it right, that switch the motors on, that switch it off, and so on and so forth.
Any 8 things that you wanted to control on the outputs, and you could sense different things on the input.
Just by simple ons and offs. Well, that's digital information. What about information that's varying continuously?
That's
analog.
Quite different, right, analog information. Another program here, if you alter the joystick control that you've got there, if you move it slowly, you'll see that as your finger goes wiggling rather badly, can't draw straight lines, can you? As your finger moves, so the computer tries to track that. Now, the position of your finger was an analog quantity. You weren't quite sure what it's going to be, but the computer had to convert that into a digital quantity so that it could display something on the screen.
Well, on the very first program, we showed some analog input, and here's what it was, and we did promise to show how it actually worked. This is a pressure pad, and it varies depending upon the pressure that I can put on it.
Come on,
there we go, 160. I'm using 2 hands, you see, it's quite strong. It's a very simple little device, but it's an analog input device, and it converts the pressure I'm putting out into a voltage. And we've got another one, if you remember, which is this one. And this is a microphone, and we can input it here, sound into it, and the graph will vary depending on the loudness of my voice, which I presume is again converted into a voltage. How do they actually work inside the machine?
Okay, well, I've got a program, needless to say, to illustrate this. The fundamental thing about analog quantities is that they vary. They don't just have ons and offs, they vary. And you can see the graph here, which represents the voltage of some signal against the time. And as you said, the microphone and the pressure pad are both producing voltages. Now, the computer samples those voltages at regular intervals, maybe every 50th of a second. And it then decides what the height of the signal is at those moments in time. And it reads those numbers in to the computer. That's an analog to digital conversion. We fed an analog signal in, and we've got a digital result to deal with.
So the accuracy of the representation of the analog input would be very dependent upon the size of the time slices. The more rapidly... You can actually see it on that original graph. When I was moving it very slowly, it gets a fair representation of moving it. When I moved it very quickly, obviously I was moving it further in the time slice that was allowed.
That's the major problem with analog devices. You must sample very frequently if you're to get an accurate representation. So 2 analog inputs there we've dealt with.
Well, what about analog output?
Okay, there are, on this computer, we've got some analog outputs set up. We've actually arranged 2 outputs. The machine can produce music, and it can also change lights. Now, lights normally go on and off in just a digital form, either on or off. But you can actually make the computer fade them up and down. Can you push some of the buttons? That's right, produces sound, which is analog, and music. Now, if you press the button slowly, you'll be able to see the lights fading up and down. Quite different from the digital world.
Well, thank you, John. And most things that can vary can be turned into electrical signals, which can be fed into the computer. And if we combine this ability to switch things on and off, we can begin to see how the computer can control, say, a robot, and do some of the things that we can do and which we take so much for granted, like moving our hands. There are 2 major differences between animals and ourselves. One is the brain, our intellect, if you like, and the other one is the hand. We can use it to hold tools, we can use it to play musical instruments, we can use it to write poetry, or we can even give signals with it. If you lose one hand, it's bad news. If you lose both hands, it's an absolute disaster. And for centuries, we've looked for artificial hands. First, it was a hook, and then a sort of clamp, which you could seize things with. It was slow, it was ugly, and nobody liked to use them. But much of the action of the hand is almost a reflex reaction. If you put something in the palm, it will clasp it. And it's in that area that we can start and make use of the power of a microcomputer. Now, here on my arm, imagine that I've lost my hand, thank goodness I haven't, but we're taking signals from the muscle on the top of my arm and the muscle on the bottom. And we can see the level of these signals by looking at the oscilloscope. By simply moving my hand like this, I get one signal, and by moving it that way, I get another signal. And of course I can have positions in between this, and this can be used to command an artificial hand. And this is quite a unique piece of equipment and very, very sophisticated in what it can do. The control you have is almost uncanny, and it can almost follow exactly the movements of my hand as I open and close them. But of course, you don't need a hand. I could do that just by tensing the muscles and relax them, tense them and relax them. In fact, it would probably be a lot easier if I hadn't got a hand on at all, but that's a little bit too far for me to go. And I can close it very gently on something and pick it up and then put it back down again and release it. So there I'm using control, I'm controlling it. But in addition to that, this hand has 10 sensors on the palm, in the fingers and in the thumb, so that it will do things quite automatically outside my control. For example, if I take this screwdriver, I touch that sensor, the hand will automatically position itself to grip it. I then take over command myself and hold, and the fist will close over it, and it's extremely simple to use. I learned to use it in a matter of minutes, and automatically you can tap away and keep control over it, and then when you've done your job, you can open up the hand and get rid of the tool. There's an even more interesting sensor on this, and that's here in the thumb, and all it is a microphone underneath this piece of Velcro. And when I want to pinch something in between the fingers, I can pick up this piece of sponge like that, and as I pull this piece of sponge out, or attempt to, the sound is transmitted from this sensor here into the computer. When it hears the sound, it automatically tenses up the hands to stop me from withdrawing this piece of sponge. In other words, it's a complete feedback mechanism. No signal from my hand is affecting it. And I can simply open the fingers and let it drop. There's another sensor here on top. We touch that sensor like that, and the thumb comes over the top of the finger, and I can place, for example, a book in there, and then go into the hold, and it holds, and it will squeeze it, and then it can hold very firmly a tray or a book that you've picked up, and you can release it like that. But quite obviously, beautiful a hand as it is, nobody's going to want to walk around carrying this huge micro. In fact, this is just a development system. It's a 16-bit machine, and what will eventually happen once the programs have been totally perfected is that a special micro will be built and put into a box that size, so it can be put into the pocket and the hand controlled very elegantly. Well, that was a fairly complex system of sensors and control mechanisms. Let's have a look at something a bit more straightforward. Well, in the first series, we ran this demonstration, and it shows the same sort of logic that we saw in the hand. If something happens, then do one thing, otherwise do something else. And in this case, we're taking the temperature by this temperature sensor, and we're feeding it into the computer and displaying the temperature's number on the screen, and also running it as a graph. If the temperature falls below a certain level, we're going to switch on a heater. If it goes above a certain level, we're going to switch on a fan. And we can see if that works. We'll put it in some ice here. Immediately the temperature graph falls and the fan heater goes on. Put it in the hot water, get an immediate rise in temperature, the heater cuts off and the fan comes on. Well, John, how does it work?
Well, first of all, we have to sense what the temperature is and convert that temperature into a voltage, or at least produce a voltage proportional to temperature. Now, this basically is the device we use. It's a little integrated circuit, and you have to have a battery outside the circuit and a few other things. And all those are put together into a device like this. So there's several components in this device. And then that plugs into the analog input at the back there. So that's a way of sensing the temperature. In fact, we could stop the program running, and I could tell it to print could you put it in the ice? Print add val 1, which will ask it to print the number that it's getting in from that input at the moment.
And presumably a higher value if you put it in the hot water.
That's right. So if we now ask it to print add val 1 again, you'll get a much higher value because there's a much higher voltage being produced by the temperature probe. So that gets it in. Now, if we have a look at the listing of the program, you'll see how we deal with those numbers. First of all, here we have temperature equals add val 1 divided by 36.5. And the 36.5 is just there to convert the number that the computer produces into a temperature in Celsius.
It's a straightforward relationship between the voltage and the temperature.
Yes, it's very linear indeed. And then down here you can see how we control the device.
Yes, I recognise this. If the temperature is less than 30 and the temperature is greater than 20, then the coordinates of 65, 120 is equal to 0.
Right. The Address 65120, you may remember, we had that address for the output port, and we have got two wires connected on to the output port, one of which controls the fan and one of which controls the heater. And if you put 0 into this byte, then both of these will be switched off.
Well, there's the next temperature. If the temperature is greater than 31, in other words, it's hot, then the condenser 65120 is equal to 1.
And in that case, a 1 would be placed here, and the fan switches on.
And if the temperature is less than 19, in other words, it's cold, condenser 65120 equals 2.
Now 2, translated into binary, we'll put a 1 in there and a 0 in there, and that will have the effect of turning the heater on, but not the fan.
Well, how does the actual output work?
Well, we use the same port that we used last time for driving the lights, but this time we instead drive the fans. You can see there are 3 leads coming off there. One is an earth connection, and the other 2 contain the signal connections to say that the fan or the heater should be switched on. And there are in fact 6 other unused connections corresponding to the 6 bits in the byte that we weren't using. Let's follow down that wire and have a look at the control box.
That's the same output port we used for those lights that were going on.
Exactly the same, that's right. We've got the control box over here, and all it does is mains comes in to the control box, as does the feed from the computer. And the feed from the computer is used to switch on and off 2 relays, one to turn the heater on and the other to turn the fan on. You see, the output from the computer only goes between 0 volts and 5 volts, and you cannot connect any mains equipment directly to the computer. You stand a good chance of blowing it up. So you must have some very good isolation, and we use relays in this case to let the computer control the mains circuit. So we've got, in effect here, a control circuit, and the computer is able to measure the temperature and control things on the output end.
Because we were showing it actually in the ice or in hot water, but normally this would be standing in the air almost like a thermostat, and you get continuous variations, so it would be a closed-loop feedback mechanism.
That's right. If you have it actually sensing the temperature of the air and then changing the temperature of the air, that's called a closed-loop feedback circuit, and that's a very fundamental, important concept.
You may have seen something like this before, being used to deal with car bombs in Northern Ireland. But when the army are using it, they control it with either a wire or by radio. This one is completely free-ranging, and in fact it's controlled using a personal microcomputer you might find in your own home. It's programmed to find out just where I am. For its eyes, or perhaps I should say its ear, it uses a sonar rangefinder that you might find on a Polaroid camera. Not only is it programmed to actually determine where I am, it's also programmed to track me, rather like a faithful dog. If we were to look at the program that's controlling this robot, we'd find instructions for some loops, which in ordinary English would sound something like this. If the object's lost, then search for it by turning round. Repeat this until it's found. Then a feedback loop. If the object is more than 1 foot away, then advance. If less than 1 foot away, then retreat. And it will go on doing this until it's told to stop. Back to something a bit less intimidating. Our bug is still trying to find its way out of the maze. The interesting thing about this is that the robot is being controlled by an artificial intelligence program. In other words, it's learning from its mistakes as it goes around the maze. But what exactly is it doing, John?
Well, as you said, Mac, it's following a very complicated program indeed. Its overall aim is to get from the start of the maze to the end of the maze, but it's programmed to be able to cope with a lot of unexpected situations on the way. For example, it might slightly miss the line, and if it does that, you'll find that it'll veer slightly to the right and slightly to the left, as in fact is doing now, until it finds itself back on the line. If we look at the screen, we can see what it's doing at any particular moment. It's turning through 90 degrees to the right to try and find another black line at the moment. Failed to find one, so it turns 90 degrees back to the left.
And all the time it's mapping out the parts of the maze that it's already visited.
That's right. So it's got in its memory a map of the maze.
And how does it do this?
Well, it's got a lot of sensors on it. In fact, there are 4 sensors on it.
So I've got another buggy here. Let's have a look at this one.
Well, there are 2 digital sensors and 2 analog sensors.
Well, clearly the buffers are the digital sensors, that's it. And it feeds out into the computer there. We can hear it given that. That's the right-hand one. There's the left-hand one.
Right, and it uses those to sense when it's hit the end stops, to know if it's actually touched something. Those are digital. They're just working micro switches underneath. That sensor there and that sensor there are both to do with light, and they are both analog sensors. This one, it uses to search for the bright light, and it's simply a resistor that changes its value, the amount of light on it.
And if I cover that, the reading will shoot
Drop
right
down
down.
to 70 odd and then up to 1,000 when it's exposed to the light. This one's really rather different. This sensor emits infrared light on this side, which is reflected off a surface, and then the infrared is picked up here. So it can follow either a white line or a black line and determine which it's on. Now, it's actually an analog device, but the computer senses whether it is above a 50% level, whether it's above grey. If it's brighter than grey, it says that must be white. If it's darker, it must be black. That type of...
Move it on there, we could possibly see that, possibly.
Yes, you can see the two different values. When it's on black, they're 1,000, and down about 500 or so when it's on the white.
Right.
Now, that type of sensor is used, in fact, to read barcodes. And you may have seen barcodes on food products and things like that. And the buggy can use these barcodes to sense where it is on the road. Quite an intelligent device. It's found the light. So it knows that the path across ahead, and it's got to turn around and back off from the light.
And it's actually marked the light on the end of the maze there, and now it's going to go and try and find the exit to the maze.
That's right. It'll have to come back all this way.
Well, those are the input devices, and we've also got some output devices here.
Right, well, we've got two output devices. There's a stepper motor here and a stepper motor over here, and as well as that, there's a device for moving the pen up and down. So, stepper motors and pen up, down.
The stepper motor just moves it around one click at a time at about 7.5 degrees.
When you give it one digital pulse, it moves, as you say, a very small angle. Now, if I make the buggy move forwards by pushing that key, you see both stepper motors go in the same direction. So the buggy moves forward. If I say to the buggy, go left, then one stepper motor goes forward and the other one goes backwards to make it go round in a circle.
And the pen there is just to trace its path on whatever it's cruising.
That's right, and there's an electromagnet which lifts that pen up and drops it down. A digital signal, again, controls that.
What's it used for?
Well, it's used really as a teaching aid. You can use it, for example, with the language logo for teaching kids how to analyse a particular problem. But you can also use it really only limited by your own imagination. It's a modular device which you can add extra sensors onto, you can add other devices onto.
And are things like this being used today in industry?
Yes, they are very much indeed.
For what sort of purpose?
Well, for example, in a number of production sites, there are little pallets that drive around a factory floor and can tell where they are by markings on the floor, and they can follow a black line to find their way around the factory.
Well, there it is. It looks as if it's just about find its way out of the maze. It's a bit hesitant there. And there it is. Well, at last it's found its way out, and it's given us some idea, at least, of the basic principles of much more complex systems actually in use in industry today, where computers are controlling hundreds of devices. And we hope to look into that in much more detail in future series. Next week, we'll be looking at moving pictures, or as some might say, Mickey Mouse graphics. Till then, goodbye.